Hello and welcome back. In this video, we're going to be exploring an example of partial derivatives in a real-world application. So here we'll use the ideal gas law that relates pressure, volume, and temperature together for an ideal gas in some container. K here, so you may be familiar with the ideal gas law as PV equals nRT. So this K is number of atoms times this R constant, which is a product. So this R then is a product of Avogadro's number and Boltzmann's constant, but those are both constants. So R is a constant, and then we're going to assume the number of atoms in this container is constant as well. So that means altogether we just have some constant times the pressure. So we'll work with this more simplified version of the ideal gas law. And let's see. So what kind of information can we get from this with partial derivatives? So let's say determine the rate of change of the pressure, that's P, with respect to volume, V, at a constant temperature. So we're going to leave temperature constant, and we want pressure with respect to volume. So I'll start with this PV equals KT. We're going to keep temperature constant, and I want pressure in terms of volume. So I'm going to go ahead and solve for pressure here. So P equals KT over V. So here we have P. If I want to maybe rewrite this to make it a little bit more explicit, P is a function of both temperature and volume. So it's a function of two variables, which means I can take partial derivatives with respect to both of these. Now in this problem, we're talking about partial derivative of pressure with respect to volume, because we're leaving temperature constant. That's how we know this is a partial derivative, is when one of the variables is being left constant. So what we want here is partial P, partial V. Or if I want, I could write this as PV. P sub V. And so that's going to be the partial with respect to volume of this equation we have here. Sorry, my K looks a little bit weird. KT over V. Now remember this V on the bottom here, that's like V to the negative 1. This might make it easier for you to differentiate. Remember, that's like V to the negative 1. So taking a derivative of this with respect to V, leaving everything else as constants, I'll get negative KT V to the minus 2, or over V squared. So that's the partial derivative of pressure with respect to volume. It represents this quantity that we're after, the rate of change of pressure with respect to volume at a constant temperature. So one thing to notice here is that, well, temperature's a positive quantity. We are in Kelvin here. This is in Kelvin. So temperature should always be positive. The volume squared is going to be positive. So this KT over V squared, this is positive. And the fact that we have negative of that means this is always going to be negative. This is always going to be less than 0. And so what that means is as volume increases, well, what do you expect to happen to the pressure? The pressure, P, decreases. And this actually gives us a little bit more information. We can see that the temperature is scaling this rate. So at a higher temperature, this rate is going to scale linearly. And then we have over V squared, which means if I'm sitting here at a really low volume, a really, really small volume, and I increase the volume by a little bit, my pressure is going to decrease drastically, right? If I have a really small volume and I increase it a little bit, pressure will decrease drastically. Whereas if I started with a big volume and increased by the same amount as I did before, the pressure wouldn't decrease as much. It would still decrease, but just not as much. So that's what I mean by interpreting the results, things like this. All right, so we do have a function here of two variables, so we might also, well, we might wonder something else. What about the rate of change of pressure with respect to temperature? So again, I have this P, this pressure function, as a function of temperature and volume. And remember that looked like KT over V. And now I want rate of change of pressure, so that's a partial derivative of P with respect to temperature, and then volume is constant there, so that's a partial. So what I'm looking for here is partial P, partial T, and so that's partial T with of KT over V. All right, well, find my T variable. It's just up here. This K over V is being treated like a constant. T is raised to the first, so I should just get K over V. Now, volume, again, is going to be a positive quantity. This K is a positive quantity, and so this is always going to be positive, greater than 0, which means as temperature increases, what happens to pressure? Pressure also increases because this is a positive rate. So I'll just say here as T increases, P also increases. And there we have it, applying partial derivatives to a real-world example that you may have seen before in a physics or chemistry class. Okay, that's it for this video. I'll see you next time.